In the last video, we looked at the abstract task of classification. In this video, we'll look at some other abstract tasks that can also be solved with machine learning. We'll start first with the other supervised task, regression, and then we'll look very briefly at some unsupervised tasks, namely clustering, density estimation, and generative modeling. But first, regression. The basic principle of regression is very simple. Where in classification we had a target that was a class, one of a small set of categories, here we have a target that is a number. So the rightmost column here in blue is our target value, and we have to predict the number given the features. So the data set constructed as before, this time with a number as a target label, is fed to a learner. The learner again produces a model, and given an instance that the model has never seen before, it can predict purely from the features a new target value. At this point, it's helpful to give the components of this picture a specific notation so that we can easily refer back to it later. So we'll refer to the feature, the vector of features of an instance as with a bold-faced X, and we'll assume that our features are numbered so that an instance that is indexed by the number I is indicated by the subscript I, and we'll refer to the true label according to our data of instance I as yi. The true label that in this case we do not know, so we have to predict. And we'll call the model f, since it's a function from this feature space to the label space. To illustrate how this might work, we'll stick with the biometrics like we did with the classification. And in this case, we'll stick just with a single feature. So we'll measure, for each of the people in our data set, we will measure the stature, the height. And our target value will be to predict the length of their legs. So this is strongly correlated to the height, so it should be easy to predict, but there's not a perfect relation, so there should be some noise as well. And again, we can plot this because we now have one feature and one numerical target. We can plot this in a two-dimensional space. Our data looks like this. Again, a cloud of points, very similar to what we saw in the classification task. But it's important to realize that where we plotted the feature space before, what we're plotting now is a combination of the feature space and the target values. The feature space here is one-dimensional because we only have one feature. So the feature space is basically the horizontal axis, and the vertical axis contains the target labels, the target values that we're trying to predict. So even though the plot looks very similar to what we saw in the previous video, it's actually fundamentally, conceptually different. Nevertheless, in this space we can also represent our model. And we can start with the same intuition that we had before. What if we simply draw a line in this space? And that looks like this. Based on a line we can build a model. We simply draw a line in this space. We start with a point in the feature space. So let's say we encounter somebody who is 180 centimeters tall. And the line that we've seen gives us a mapping from that value to the target value and gives us a suggestion that according to this particular line, to this particular model, we can expect a leg height of around 102 centimeters. Of course, we could have drawn a different line, and this isn't a particular good line for this data set, so we need to follow the same logic that we did earlier. Given the space of all possible lines that we could draw, how do we define what constitutes a good fit? What is our loss function for this model space? And the loss function that we often use for regression is what's called the mean squared error loss. So basically, we take some function f, some model, one of these lines that we've drawn. We look at, for all the instances in our data set, what the model predicts. And we subtract from that the actual value that we know. So this is the blue part in this formula. How wrong, essentially, how far away our model prediction is from the true value. We square that, and then we sum it for all values in our data set, and possibly divide it by n, the number of instances in our data set, so that we get the average mean squared error. So you can visualize that a little bit like this. Here the orange dots are the values in our data set. The line is our model. The blue bars give us the absolute difference between the prediction of the line and what our data set actually says. We square these values and then sum them up, and that gives us an indication of how poorly our data does. There are many reasons why we square the difference between the model output and the true label. We'll go into this in more detail in the next lecture. But note that if we didn't, then if we had a large positive error and a large negative error for two different instances, these would cancel out against each other and give us a low loss. So that's one reason to square it, is to prevent this kind of effect. And if we look for the line that minimizes the mean squared error loss, we end up with this. So this is, for our data set, the best linear regression fit, the model that best fits the data under this loss function. We can also take the principle of a tree-based model. So we saw a decision tree to use for classification. We can also use a regression tree, which essentially builds a tree, splits on the value of the feature at every node, and once it hits a leaf node, outputs a particular constant value for that leaf node. It gives you a model that looks a bit like this. And we can also apply the k nearest neighbor principle to regression, which gives us a model that for a new instance looks at instances that are nearby in feature space and averages their value. And that gives us a model that looks like this, if we set k to 7 in this case. So that's all we'll say in this video about regression. Now, to finish up, let's look at some unsupervised abstract tasks. First up is clustering. Clustering is a lot like classification. We divide the data set or the feature space into a set of finite values, but the difference is that in this case we are not given target values. So we are given features, but no classes, and the learner has to decide purely based on patterns found in this set of features how to separate the data set into different clusters. So for a new unseen instance, we assign it to a cluster without knowing beforehand what kind of clusters are in the data. Let's look at a quick example of a very simple clustering algorithm to see how this is done in practice. This algorithm we see here is called k-means, not to be confused with k nearest neighbors. And in this example, we will separate the data set shown into 3 clusters. And the value of 3 clusters is, again, like in k nearest neighbors, a hyperparameter that we have to choose beforehand. And the way k-means operates is that it first chooses 3 random values, in this case, in picture B, the blue, green, and red points, and it colors all the points in the data according to which of these 3 means is the closest. So this coloring you see in picture C. That gives us an initial clustering, a fairly random or a very arbitrary clustering of the data into blue, green, and red points. And in picture D, we then recompute the locations of these mean values by averaging the locations of all the points. So you see that in picture D, the blue point is now moved to the center of all the blue points, the green point is moved to the center of all the green points, and the red point is moved to the center of all the red points. We then recolor the points according to which mean they are closest to, and we iterate these 2 steps. We recompute the means, recolor the points, recompute the means, and so on. And what you see is that at the end, the means converge to centers for natural clusters in the dataset. And so we have separated the feature space into 3 very natural clustering regions: the blue, the green, and the red. Another unsupervised task that is a lot like clustering is density estimation. Here again, we get a data set of instances represented by features in which the learner discovers patterns of density in feature space, but this time the task of the learner is to produce a model that outputs a number, and that number should indicate whether that instance is likely according to the distribution of the data. So if the instance we're being fed is very much like the points that we saw in the data, then the number is high. And if the instance is unusual compared to the data, then the number is low. And in general, we add some constraints to make sure that this value that is output by the model is either a probability if the features are categorical, or a probability density if the features are numerical. And if this sounds abstract, you can think of simply something like fitting a normal distribution to a set of numbers. For instance, here are the grades from the course as taught in 2017, represented as a histogram. And if you know a little bit of statistics, then you can easily fit a normal distribution to this. And that normal distribution is essentially a density estimator, because it gives us, for every point in this one-dimensional feature space, it tells us how likely we are to see one of these grades fall in that area of feature space. Of course, if you look closely at this distribution, it's not really a normal distribution. It's much better represented by a distribution with 3 peaks instead of a distribution with 1 peak. Likely this corresponds to the 3 different student populations from different programs that took part in the course in 2017. So one thing you can do, instead of fitting 1 normal distribution to this data, is fit a combination of 3 normal distributions to this data. This gives you a more powerful model that can represent more shapes of density over the feature space, but it's also a model that is more difficult to fit. And we'll look at these kinds of models in the later lectures. If your model becomes even more complicated, then it's often no longer possible to give good estimates of the density in feature space, and the only thing you can do is sample more likely points from your model, sample points that are like the data that you've seen. Here is a very powerful example of that, because these people that you see here are people that don't exist. These people were generated by a model that was fed a large set of high-resolution images of people, 70,000 in total, and based on that it learned a probability distribution on the space of pictures that corresponded to its input data. In other words, it learned a probability distribution from which we can sample new faces. And if you click on the link in the bottom here, you will see that in action, and you can actually generate as many new people that don't exist as you like. This is what we call generative modeling, a model that learns a probability distribution, quite a powerful distribution, but usually one that you can only sample from. So these are the 3 unsupervised abstract tasks that I wanted to discuss: clustering, density estimation, and generative modeling. And to finish up, we'll look at some abstract tasks that are a little bit in between the supervised and the semi-supervised tasks. For instance, one thing that is common is semi-supervised learning. In semi-supervised learning, we combine supervised and unsupervised learning, and we define a setting where we have a small set of labeled data and a large set of unlabeled data. So here on the right, we have a large set of data from the same domain, but only a small proportion of the digits are labeled. This is very common because in many cases, unlabeled data is very cheap to gather. We can usually crawl it off the internet or download it in bulk. But labeling is something that has to be done by hand, by people, so that's very expensive to do. So if we have a small set of labeled data, and we can append to that a large set of unlabeled data in such a way that it makes the classifier more effective, that's usually a very cheap way to boost our performance. To give you one example of how this might be done, we can look at self-training, which is probably the simplest instance of semi-supervised learning. And self-training works simply by training a classifier C first only on the labeled data. As we've done before, pick any classifier you like, and then we enter a loop. We label the unlabeled data with the classifier that we've learned, and then we retrain a classifier on the combination of the unlabeled data with our predicted labels and the original label data. And in practice, this quite often works to build better classifiers than we would have had if we had trained on the labeled data alone. In recent years, another phrase has cropped up, which is self-supervised learning. It's not quite clear yet what precisely is meant by this, but in general it refers to ways in which a large unlabeled dataset can be used to train a model without requiring a large amount of manual annotation. One example that we see here in the domain of natural language processing is where we feed a model that can read and produce sequences, a sentence with one or more words masked out. And the goal of this model is to predict what is in the masked out word. This is not in itself a useful task, but it is a task that can be performed on unlabeled data. And a model that can learn to do this well has likely learned a lot about the structure of sentences. which means it can then be used to build on for other more useful tasks, possibly with a small amount of labeled data thrown in. Semi-supervised learning and self-supervised learning have a lot in common, and it's not quite clear where one begins and the other ends. But in general, self-supervised learning tends to refer to deep learning models and to clever training schemes using unlabeled data. And we'll see some more examples when we start talking about deep learning in more detail. So, looking back over the past two videos, what have we learned about the abstract tasks of machine learning? We can follow the following flowchart. If we need to learn to interact with the world and take actions as we are learning, then we need to look at reinforcement learning, which we look at in the end of the course. If we don't need to interact with the world, but we do need to learn and predict at the same time, then we need to look at online learning, which we won't look at in this course. If we don't need online learning, then it's best to look at offline learning, where we separate the learning and the predicting. If we have example input and output, then we can apply supervised learning or semi-supervised learning if we have some extra unlabeled data. And the prime examples of that are classification and regression. If we don't have example inputs and outputs, we can look at self-supervised learning, or we can look at unsupervised learning such as clustering, density estimation, or generative modeling. In this lecture series, as I noted before, we will spend most of our time looking at supervised learning of the types of classification and regression, but towards the end of the lecture series we'll also look a little bit at reinforcement learning and some of these more deep learning type tasks like self-supervised learning. In the next video we'll take a broader view and we'll look at the social impact that occurs when machine learning methods are used in the real world. This is becoming more and more of a relevant question as machine learning grows up and becomes used more and more in actual products and actual software that we use every day. And as such, it's becoming more and more important to think carefully about what the consequences are of using this kind of software in the real world. We'll look at that throughout the lecture, and we'll start in the next video by looking at the example of gender or sex classification that we've used so far in these videos.